The next topic is pole placement. Why do we need to do the pole placement? To improve the performance of a system, we'll add some external components that can be adjustable. Okay, so here is an example. So here you have a system, that's an open loop system. Okay, so we don't know what is the performance of the system, but if we want to improve it, what we can do, we can make it as a closed loop system by adding a feedback loop. Okay, here I added a feedback loop. Now in this feedback loop, u equal to r minus f. F is the feedback times y. Okay, so here what we are doing, we are placing the poles to adjust the performance of this output or improve the performance of that system. Okay, improving the performance means we are controlling the system in a better way. That's what it meant. So here in this feedback system, it's called feedback controller design. What I'm doing, I'm taking the feedback from the output. Okay, the output feedback controller design will allow us to adjust the performance without changing the original parameters. So basically, if you look into any system, sometimes you might not have access to this box inside this box. Okay, so but definitely you will have access to your output, definitely you have access to your input. So without disturbing this system, without opening the system, because either you do not have access to it or you don't want to mess with it, what we are doing, we're designing other system, a small feedback system from the output. We call it as a feedback controller design. Okay, another way of another design is state feedback design. Okay, so if we have access to the states, x1, x2, x3 state variable, so if you have those state variable access, then we can take that state variable and then design another feedback to get to improve the performance of that system. So here u equal to minus fx. F is the feedback, x is the state variable, plus r. Okay, so if you have n number of state variables, then you will have f number of we can say the feedback parameters. Okay, so now say x dot equal to ax plus bu, y equal to cx plus du. Those are the open loop system state equation and output equation. These are the state equation and output equation for a given system. Assuming that's an open loop system. It could be closed loop system too. I don't care what is there inside this box. So here inside this box, it could be a closed loop system. Okay, but I don't care about this. What I'm seeing, all I'm seeing, here is my output, here is my input. So I'm talking that as an open loop system. Now I'm designing feedback to this system. Since I'm designing the feedback to that system, x dot equal to ax plus bu, now I just have u equal to minus fx plus r. U equal to minus fx plus r. So ax plus b minus fx plus r. From that I came up with a new A matrix. That new A matrix equal to A minus FB. Now determinant of Si minus AC is called characteristic polynomial, and if you make it equal to 0, determinant of Si minus AC equal to 0, we call that as characteristic polynomial equation. Now the roots of the characteristic polynomial equation are the poles of the system. Okay, so the roots of the characteristic polynomial equation will give you the poles of the system. Now we can improve the performance of the system by using state feedback better than using the output feedback, because we have access to more information. So one of the important point here, we can do a better control by using state feedback design, because we have more number of variables. That means we have more information than output feedback control, because output I have only one output, but states I have n number of states. So here, based on this, we can improve the performance of the system using state feedback better than using output feedback, because we have access to more information. Now, say a single pole system, h of s equal to 1 over s minus 2. So 1 over s minus 2, this is nothing but characteristic polynomial equation or characteristic polynomial. When I make it equal to 0, s minus 2 equal to 0, that's a characteristic polynomial equation, s equal to 2 in this case. So 2 is right there. We know that the system is unstable. We know a system is going to be stable if and only if I have poles on this left hand side of this y-axis. Okay, if you see, if we convert this into Laplace domain or in time domain, h of t equal to e to the power of 2t. E to the power of 2t is this is the graph for the e to the power of 2t. So since it's positive t, as time increases, it's going up, so it's unstable system. At the same time, if you have h of s equal to 1 over s plus 2, so h of t equal to e to the power of minus 2t. So e to the power of minus 2t is, see, it is stabilizing after some time. It's a stable system. So, and s equal to minus 2, basically minus 2 is going to be somewhere there. So this pole is in the shaded area or left hand side of the y-axis, so that system is stable. Now if we have 1 over s plus 20, okay, so that means e to the power of minus 20. So what makes this constant? How this constant makes the difference in the system, that makes how fast the system is going to settle down. So e to the power of minus 20 will settle down a little bit faster than e to the power of minus 2. So basically what I'm saying, so if you look into this graph, e to the so minus 20 is somewhere there. So if we have a pole which is far away from the origin, then that system is going to settle faster than a system which has pole closer to the origin. That's what it says. So the performance of the system depends upon the location of the pole. So those are 22, those are the poles. So as I mentioned, if a pole is far away from the origin, that is more that will stabilize faster, and we can adjust the performance by ensuring that poles are placed at a desired location. So you can design a system by choosing, oh okay, I want a pole at minus 20 or minus 15 based on how much time you have to settle down. Okay. This is about the pole placement. So I'm going to start solving an example. I'll stop this video here. I'll continue in the next video. Thank you.